Domain 1, Task 1.3 of the Claude Certified Architect exam tests a specific engineering skill, configuring subagent orchestration. Claude invokes subagents as standard tool calls, requiring specific JSON configurations to trigger delegation. Misconfiguring these SDK boundaries results in silent execution failures, where the system attempts to process tasks without delegating them. We are going to look strictly at the API mechanics, the context boundaries, and the session management required to prevent those failures. Precision in these configurations determines whether you build a functional multi-agent system or fail the exam scenarios entirely. The architecture relies on a central coordinator. When a workload arrives, the coordinator evaluates the requirements against its available options. It can only delegate work to subagents through a specific tool calling mechanism. This split-pane logic diagram shows a JSON API payload on the left and coordinator behavior on the right. Delegation is gated by the allowed tools array. If empty, nothing spawns. This triggers a silent non-delegation failure. No error is thrown. The coordinator simply does the work itself. To enable delegation, you must explicitly include the spawning tool. Historically, this tool was named Task. In newer SDKs, it is named Agent. The exam vocabulary relies entirely on the term task. However, your actual detection and monitoring code must be written to match both names to catch system init events and permission denials. Including this spawning tool in the array also acts as an auto-approval mechanism, bypassing standard permission prompts for subagent invocations. You must never place the task tool inside a subagent's own tool array. This is an absolute architectural rule, designed to prevent infinite recursive spawning loops. Failing to strictly define the spawning mechanism forces all execution through a monolithic bottleneck, defeating the purpose of your agentic architecture. Once a subagent is successfully spawned, we have to track the data flow across the strict boundary separating the parent coordinator and the child. This diagram illustrates a boundary wall separating a coordinator and subagent. They inherit no parent history. File paths and errors bounce off, remaining isolated. Data only moves across by explicitly packaging these variables inside a structured prompt string passing through the wall. Every time a subagent is invoked, it initializes with a completely fresh system prompt. The return path is equally constrained. Only the subagent's final message returns to the parent. This egress message is passed verbatim back to the coordinator, functioning exactly as a standard tool result. Multiple sequential subagent invocations share no memory unless their inputs and outputs are manually wired through the prompt. Treating subagents as extensions of the coordinator's memory, rather than isolated stateless functions, guarantees hallucination and execution failure. The behavior and constraints of these isolated functions are configured using the agent definition object, a programmatic blueprint mapping a specific name to a configuration. Within this blueprint, the description field directly drives the coordinator's internal routing logic, dictating exactly when a specific agent should be called. This diagram shows the agent definition JSON schema's tools array, your primary lever for enforcing least privilege. A reviewer profile is restricted to read-only operations, but a test runner profile expands its access scope by adding the bash tool. The blueprint also contains a model field, allowing you to override the system default for a specific worker. This enables a standard architectural pattern where a highly capable Opus model acts as the coordinator, managing faster, specialized Sonnet or Haiku worker models. By strictly defining the prompt, the capabilities and tools, and the specific model, you build a specialized, secure worker module. As agents operate, state is managed through sessions. A session is the persisted conversation history, automatically written to a local JSON-L file on your disk. To return to a previous state, continue reloads the most recent session in the directory, while resume targets a specific session by its unique ID. The third method is the fork command, which allows the system to split and explore divergent analytical approaches from a single starting point. Calling a fork copies the original session history to establish a shared baseline, then generates a completely new session ID for the branch. This diagram illustrates an exam trap. Forks isolate conversation history, but operate over a single shared directory on the file system. If one branch makes a file edit, that change is real, permanent, and immediately visible to all other parallel sessions. There is no built-in API mechanism to merge these branches. Consolidation must be engineered entirely at the application level. This isolated session state ties directly into the mechanics of true parallel execution. To run independent subagents concurrently, you must emit multiple task calls simultaneously within a single coordinator response, rather than serializing them across sequential turns. Properly structuring your session state and concurrency models scales your system's capabilities horizontally, avoiding context drift and file conflicts entirely. Let's summarize the architectural truths established. Invocation relies on tools, context requires explicit passing, and capabilities demand strict scoping. If your coordinator refuses to delegate and does the work itself, verify that the allowed tools array contains the task tool. If a subagent is missing necessary facts, verify that you explicitly injected that data into the tool's prompt string. To execute 3 divergent strategies efficiently, load your baseline analysis once and execute the fork command 3 times. Subagent orchestration demands explicit configuration at every boundary. Mastering these programmatic limits ensures execution reliability and secures your path through the CCA exam.